Hi everyone, my name is Stephen Weigel, and in this video, I'm going to clarify on something that I briefly mentioned in video 3 regarding the transition from permutations to normal orders using transpositionally symmetrical sets that have more than one factor in common. Recall that this equation for a scalar class set tells us the number of permutations always for any scalar class set. Now, transpositional symmetry in a set only affects the number of normal orders. Confession: I explained a way to figure out the number of normal orders from a transpositionally symmetrical set with one factor, but instead of expanding the rule to sets with more than one factor, I provided a quick preview of those problems without actually talking about the compounded rule involved. Since then, I have refined what I already know into a much superior method for understanding, and I still haven't actually found out the analog in group theory. This is all stuff I figured out on my own. So now I'm going to explain the transpositionally symmetrical phenomenon again with this superior method presented to you. We'll go through a few examples of sets to normal orders, and we will employ a more consistent format for all of the problems. And I'll use color coding, using a different color for each scalar class set to help sort out all the nesting. Okay, so here's a non-transpositionally symmetrical set. 4L, 3S, or 3L, 4S, doesn't matter where the step sizes are. And you know what? From now on in this video, I won't name which one is L and which one is S. Okay? So, 4, 3. Here is the number of permutations, which, when divided by the total number of tones, equals the number of normal orders. In future problems, this top right area will help clarify any number of ways that a set can divide, the number of permutations each nested set has, and how the nested sets all relate to each other. Alright, so now that easy example is over, here's our second example, a transpositionally symmetrical set with only one factor in common between the two step sizes. With this transpositionally symmetrical set, 4, 2, we write out the permutations as different terms that add together, writing how they are nested in the top right-hand corner. The first term will represent the original set's number of permutations with all of its nested sets subtracted. And the second term will represent the largest nested set's number of permutations with all of its nested sets subtracted, etc. This one is easy because, since there's only one factor in common, only the first term / permutation has anything subtracted from it. And since that produces only one nested set, there are also only two terms, the original set and the nested set. We'll start with the first term, and this again represents the number of permutations in the original set, 4, 2, subtracted by all of the permutations of its nested sets, which in this case is just 2, 1. This is because 4, 2 only divides by 2, and that's it. Of course, 1 doesn't count. So the permutations of 2, 1 are subtracted from the permutations of 4, 2. Well, that gets rid of the symmetry inherent within 4, 2, and it comprises the first term in our little sequence of adding permutations. Now this second term here, this will be the number of permutations of the set 2, 1, our first and only nested set. This equals 3 because we can't subtract any more permutations from 2, 1. And now notice that these two terms, when added, amount to the same overall number of permutations that we had originally, which is correct. It's just that now the permutations have been split into groups, or terms, and once this happens, we are ready to divide each term by the total number of tones from each term's set. So for term 1, our original set 4, 2, we divide by 6, and for term 2, our first and only nested set 2, 1, we divide by 3. And now we add these divided terms to get the number of total normal orders, which we see is 3. Do you see how this new method allows a consistent procedure of subtraction on each term, yet what is subtracted adds back up in the equation? It's so that the permutations are grouped properly. Incidentally, you can also check your subtractions by adding up all the permutation terms and seeing if they equal the number of permutations in the original set. Now let's try a set with more than one factor in common, and we will keep the same procedure. 4, 4 is a good set to try, as this set is divisible by two factors, which are 2 and 4. So, in seeing all the ways this set can divide, we have a few choices. Our 3 terms are going to represent the original set and the 2 different nested sets, and viewing this relationship is aided with our little drawing, see in the top. The first term will represent 4, 4, the second 2, 2, and the third 1, 1. Now with each term, we need to subtract all of the possible nested permutations from each. This means that for 4, 4, our first term, we need to subtract the permutations of 2, 2 first. And you can see that the numbers of permutations are just written by each of the sets, nested and original, for reference. But 2, 2 can also divide by 2 to produce 1, 1, meaning that it also has to be subtracted by 1, 1's permutations within this term. So in the first term, we have 4, 4's permutations subtracted by 2, 2's, including 1, 1, subtracted by 1, 1's. It's as if this whole drawing in the right-hand corner has been put here into the first term, or at least it's an analog. It's an analog to the adding of the terms and the first term. We just have to be thinking ahead so that every term is subtracted by all of the nested sets that are possible. The first term represented 4, 4, so the second term represents 2, 2. The only nested set in 2, 2 is 1, 1, so that is subtracted, and then we have our second term. And then the final term is just an additional 1, 1. Now that all of these terms are separate, we can divide by the number of tones for each separate term, getting the number of normal orders per set. And then we just add them up to get our total normal orders. So dividing the tones is the easiest part because it's after all of the crazy subtraction. Let's do one more example, the dreaded 6, 6. Now, this set has 3 factors in common, which of course are 6, 3, and 2. Before we dive in, let's make this little drawing again. So now we see how everything is nested, and basically the entire drawing represents the elaborate subtraction of our first term. The first term always has the most elaborate subtraction because it contains all of the nested sets. So we have 4 terms, one for 6, 6, one for 3, 3, one for 2, 2, and one for 1, 1. Okay, so here's how we subtract the 6, 6 term. We subtract permutations of the nested sets from the original, and since 3, 3, and 2, 2 both have a nested 1, 1 set in them, we subtract 2 from each of those terms as well. Perfect. Now the other terms are pretty simple as well, subtracting 1, 1 from those next two, and now we have our permutations grouped properly. Now let's just divide them all by their respective numbers of tones, then add as usual, and here's the number of normal orders. Hooray! Here's another little demo that might help. Let me do a quick explanation about the nature of such an operation. In 4-4, for example, can't we just think of the transpositionally symmetrical normal orders? That's pretty easy, right? We can just write them out. Now, when we group the normal orders by how they are divided, we get redundancies where the same set, the 1-1, can be divided in different ways, or where it counts as other sets. It can be divided into 4, or it can be divided into 2. A 1-1 can also count as a 4-4 or 2-2 here as well. The same kind of thing is true for 6-6. We see how the alternating LS set, also the moment of symmetry, can be divided into 3, into 2, and into 6. And this physical phenomenon that you see, the multiple appearances of 1-1, this is why 1-1 has to be subtracted out multiple times in these sets, because it is a result of so many different divisions, and this would be true for anything where the factors worked out as such. In fact, drawing out these transpositionally symmetrical normal orders was finally how I figured out the method for subtraction, because once you think about how the normal orders are taken away, it makes sense, and then you can reverse engineer how the permutations come from that. Well, I hope you learned a lot. In fact, I have a personal challenge for you. Can you solve for the total number of normal orders in the set 20L, 20S? Ooh, 20/20 vision. This is a difficult but manageable one, and a good way to test your skills if you want to understand the process. If you want to see the answer and how I showed my work, stick around for about 10 seconds to see the end of this video where I solve 20/20. So it looks like 20L, 20S has 3,446,167,860 normal orders. Ouch.